Hi everyone, welcome to this special session to the Colegio Complutense. This warm afternoon in Cambridge. It's warm or hot, or close to hot, late afternoon in Cambridge. So the seminar for today is devoted to and the exceptional creative generation and voice synthesis. And the speaker is Mateo Cámara, and postdoctoral research at the Technical University in Madrid, now in the MIT. And you can say that that's also this topic. Thank you, Mateo, for sharing your words with us. Thank you, people attending. Thank you, people connecting online. So, I usually get to Mateo. Start.
Thank you. Thank you for bridge shares again. All right. The permission of the public, since we all speak Spanish, and I am aware that the people joining.
Yeah, true. I think they're too connected, but yes, I don't know.
These are my parents, my friend. I'm very sure they speak Spanish. So voy a cambiar al español. Mira, voy a comenzar con una pregunta. No sé si os habéis fijado, pero siempre que pensamos en la inteligencia artificial, pensamos en la generación de texto, pensamos en la generación de imagen, pero rara vez pensamos en la generación de sonido. Y eso que la generación de sonido ahora se está volviendo bastante popular. De hecho, aquí en Cambridge, aquí al lado, tenemos los headquarters de Suno, que son las empresas así. No sé si habéis creado alguna vez una canción con inteligencia artificial, pero está aquí al lado. Pero sí, normalmente no pensamos tanto en el sonido. Y yo tengo una opinión al respecto, que creo que os voy a transmitir a lo largo de esta conferencia. Además de esta opinión que os voy a compartir, os voy a dar una serie de pinceladas sobre cómo las personas que nos dedicamos a trabajar con sonido en la inteligencia artificial, problemas que nos tenemos que encontrar, las aproximaciones que normalmente hacemos y bueno, los resultados que tenemos que hoy los vamos a escuchar. Vais a ver que van a ser bastante divertidos. Entonces, lo primero que hay que entender es qué es el sonido. Si queremos trabajar en sonido en la inteligencia artificial. A ver, todo el mundo sabe que el sonido pues es una onda mecánica que se transmite por el aire, que tiene compresión, rarefacción, que llega hasta el oído, que los órganos son capaces de entender, que emite una serie de pulsos electromagnéticos al cerebro y nosotros interpretamos, disfrutamos de la música, entendemos el mensaje que una persona está diciendo. Pero no, yo quiero hablar hoy de dos características del sonido muy concretas y que son súper importantes para la inteligencia artificial. Y la primera es que somos endiabladamente buenos detectando cualquier pequeño detalle del sonido. No lo pasamos por alto. Siempre lo vamos a escuchar. Y os voy a poner una. Fijaos. Hey, Colin, do you want me to continue in Spanish?
And you are.
English. All right. So, I was talking that the ear, the auditory system, is very precise at detecting any kind of event. So I'm going to give you an example. This is a beat, right? This noise, right? And now I'm going to play a room full of people, which is something that you consider like white noise. Right? And I've placed this same beat somewhere in the sound. It's almost an accident. But I'm pretty sure, and I challenge you, you're gonna listen to this. Did you? Yeah, it was very massive. So this is something that we need to understand. Sound, we're very, very good at detecting this kind of events. And this was just noise. Imagine AI would generate something that is noisy at some point. We would have liked them. I'd like to tell my students that the ear, the auditory system, it's impossible to fool. But the eye, in comparison, it's very easy to fool. Take a look at this image. Oh, well, you cannot see it very well. This is from the 1970 film. I took it from Netflix. Maybe you cannot see it, but here, in the sky, because of the projector, but you can see some waves, right? It's not uniform. That's something that Netflix does to save bandwidth. So it's cheaper to get the image to your laptop or to the TV. And it's something that I could be watching this film and having these kind of artifacts in the image. And I wouldn't mind. I can stand them. It's fine. I wouldn't have headache at the end of the film. However, what happens if every 5 seconds we have to noise that we hear? I could not stand it at all. I would hate it. It would stop at all. So that's another point that we need to understand about sound. We need to be super precise at generating it. I like to say that it's very easy to fool the eye and very difficult to fool the ear. But sometimes, and this is like an optical illusion but for sound, we may find that they trick us. I don't know if you have played Super Mario 64 in the Nintendo, but you may have encountered these studs that have no limit. You just continue and continue if you don't have enough stops. So the sound does. You will listen to it. It will continue increasing and increasing the pitch with no limit. How is that possible? I will explain that. Forever. So sometimes we can trick the eye, but not in quality. Only in this kind of cases. This is just a trick. It's called the set part effect. It's just a trick. In terms of quality, it's impossible to fool with the PDF. That's the first point. Second point. Sound is massive. It's enormous. We can compare it with the image and the text. For example, text, one full book could be around 50,000 words, 250,000 characters. That's not that much. Think about the this AI Gemini from Google. They have 1 million tokens in their context window. We could fit 4 books there. It's not that big. Image, this is HD quality of an image, 800,000 pixels. Still, it's something that we could fit every single pixel. Could be in the context window of an AI like Gemini. Sound. 1 second of sound in CD quality is 44.1 K sounds. And it's just 1 second. It's nothing. I mean, if I want to listen to a song, 1 minute and a half, 2 minutes, that's 4 minutes. If I'm having a conversation on my phone for 20 minutes, it's not that at all. That would be 40 million tokens. So it's invested. It's very difficult to work with because of this reason as well. That means that if over years very precise at detecting artifacts, and we have 40 million tokens, we don't have 40 million tokens, we have 40 million problems. So, yeah, challenging. That's the idea I would like to share with you. And if you remember the first question that I posed to you, why is it not that popular to work with sound? Have AI in sound reaction. It's because of this. It's so challenging that research, I would say, it's like 1.5 years behind image or text technology. That's my personal take. You can have it right. All right. So now that we know what is sound, let's talk about what to work with sound in AI. This is something usually, because it's massive information, we usually need to reduce it some way. This is something that in telecommunications engineer we are very used to. Is the idea of coding, decoding, the idea of converting something that is very big into something that is smaller, so we can decode it back to that original shape, to that original big file or big sound or big whatever. This is what we have in this structure. I like to define this. I mean, coding is not that uncommon in real life. You think? Coding something like a piece of music, classical music with hundreds of instruments. It's a very complicated signal, but it's something that we can write down in a pentagram with notes, with timbre, instrument. That's coding. I'd like to, my students, I'd like to say this is like a cheating exam. This is the book. We convert the book into only the most important information that exists in the book, so I can pass the exam at the end. So in the end, I will have something that is close to the book. It can't be the same because we have lost some information, but it's close to what we have already. But imagine that now these are neural networks. We train it with a lot of information, a lot of sounds, a lot of speech, a lot of whatever, sound effects. That means that in here, we won't have something that we can understand anymore. It won't be the note. It would be the movement. It would be something mathematically described that will be enough information to recover back the sound. But it's only understandable for the machine. That's why we call it vagrant. This is like a palabra como means nothing. Means that I can understand. I have no idea what's silent. But it's enough of it. It what makes the audio to be the audio. That means that once we have trained this, we can get good of synchron. We just need to play with this. So since this is a distribution, this is a mathematical distribution, we can take samples. And samples mean taking new data. And new data that can be decoded into something. What something? Sound. Completely new sound. Based on what we train this neural network. That's one of the ways we usually work with sound in AI, and I'm going to demonstrate to you a way in which we can sample this latent space to generate new things. So it could be, in my opinion, more or less impressive. Let me give you this example. This is one of the first things that I do during my PhD. This is the latent space projected into a two-dimensional space. And these bubbles are three different sounds that exist in reality. These are strokes against glass, metal, wood. So every time that I click somewhere in the middle, I will generate a completely new sound that will be a mix of these three. The closer it is to one of the bubbles, the closer it will resemble the bubble. So if this was wood, here it would be very close to wood. Yeah. And here very close to metal. But you can use that. Or just in the middle, which will be a mix of glass, metal, and wood. So these are things that don't exist in reality. I mean, have you ever seen a material, a mix of glass and wood? That's something that we can do with the eye, but we cannot have in reality. Another example that blew my mind when I listened to it. You know the sound of a water flow. What happens if we mix the properties of the sound of material like water and the properties of the sound, the physical movement, for example, a ball rolling, then we will have a rolling water drop, something that is impossible to exist in reality. What does it sound like? Here it's water, and you can feel something rolling. I mean, you may argue that this is just a trick, somewhere on the phone. Not. So yeah. And what things can we do with this? And of course, it's just curiosity. It's fun. In video games, this is very popular. In video games, we can use it to avoid something that is called the machine gun effect. I don't know if you have played For example, Skyrim, The Legend of Zelda, it's kind of games that every time that you are walking in some field, you may listen to a bird, and it's always the same bird. Always. It doesn't matter what you are in the game. It doesn't matter what you are in the game. Always the same. That's not reality. If you are stepping, it's always the same steps. Even though my steps were not the same. They didn't seem like the same, right? Because they were different. Reality is very clear. That's something that we can get with AI. Remember, if we sample very near to each other in the previous demonstration, we will sample something that is very similar, but different enough, like in reality. And I've used this to summarize the footsteps in Prince of Persia 2. You can see that I like all games. This is real. And I play with different types of boots. Now, it wasn't in Java. And now I'm mixing Java with good because that's the only really. Well, this is one of the things that we can do with this kind of AI. Producing live new sounds, so we avoid machine gun attacks. What other things can we do? And this is a field of about University of we can use it for film. We can use it to create the sound effects in the film. And let me share with you one of the milestones that we got when I was doing my PhD. We developed for the first time in Spain, full film that was completely made in Spain that for the first time used AI in the sound effects. So it was like 2 or 3 years ago. And let me show you the trailer, and you can see that they are giving a lot of importance to the sound because, of course, it was very, very important.
Por favor, no me tenga miedo.
Yeah, that was made by me. I'm in the credits. You cannot imagine how difficult it is to understand the decisions of a director. Because I'm an engineer, I don't speak their language. He was saying, no, but I don't want it to be like a lightsaber. Okay. By the way, sorry, let me explain something. The steel, the atom, is that piece of whatever material he was holding, and it represents the result. And it has the sound, it has the color. But he told me it can't be a lightsaber. It can't be electromagnetic. It needs to be something different. So you know what I did? I took a lot of different sounds, like I don't know, submarines, sonars of submarines, light bulbs, matches, kind of birds, whatever, waterish sound, and I put them all of them this cocktail of AI, and we were just sampling them. Do you like this one? No, more water. Do you like this one? Ooh, that's what it's good. And then you got the same song. And I want to share the experience that I had with the director with the next demonstration. By the way, we didn't use the same app that I showed you before. We used something called Brave. And this is made by a French institute. And I would like to share with you because what we are going to do now is that we are going to convert my hands and my mouth into an acoustic drum. Let's see if it works. I'm not going to have to use it out. Beatbox. No. This is going to be AI. example, this two-dimensional map that we saw before with my voice. And every time that I was speaking here, it was going through the microphone and producing these drums. I'm not that good musician, as you can see, but this is the idea of how we develop the AI, the sound text for the AI that I showed you. Okay. So we talk about sound. But this is one very specific sound that we are very interested in. And especially me, right now, because I'm using it to express the ideas that I have in my mind, put them in your heads. And that's speech. Speech is very special because we are very precise at listening sounds and very tiny artifacts. We are also very precise at understanding the emotions of someone, and understanding what someone is saying in the language or whatever. Some of the properties that the speech has is this four. These are the main ones. The outer space would be my voice, your voice, whatever voice. The duration is not the same to speak slowly, very fast. Grossly, it's not the same to be affirmative, negative, question, or the discourse. I'm talking about sound in the AI, not about the. So these things is something that we have very count, and that we have developed some researchers and colleagues during the years for something that I'm very surprised about, which is the voice cloning. Because if you are aware of my audio space and the duration I usually do, and my diversity, then you can clone my voice. And this was one of the latest research that I did in my PhD. Specifically, it's something that I thought for the very last day of my PhD defense. Because I'm gonna tell a personal story, but my grandfather wanted to visit me in my defense. But my grandfather doesn't speak English. Wants to listen to me. He's not very good at technology. So what we did was, okay, we can set up a simultaneous translation system, right? That will be using someone else's voice. So I can clone my voice with that system, and leveraging my knowledge in telecommunications engineer, I put it in a radio station here, and I place it on the very end of the commercial bands, so he could use his radio device that he's very used to use. And today I'm going to show you my clone voice. We are not going to translate exactly what I'm saying. We are just going to change the code. So we can ask it, and he will reply. Mateo both will reply. Tell me a joke.
Parece que tienes algo en mente. ¿Quieres compartirlo? Estoy aquí para escuchar.
No, tell me a joke.
Claro, aquí va uno. ¿Por qué los pájaros no usan Facebook? Porque ya tienen Twitter. Espero que te haya sacado una sonrisa. Si quieres escuchar otro, dímelo.
Okay, no. So, you can notice this is my voice. More or less. Grossly is not perfect, duration is not perfect. I mean, that's why this is research ongoing, right? But you can feel there's something that resonates. And that's where I want to get here. Because this is my personal hypothesis. This is what took me to MIT. I feel there's something lacking in the AI of today that we need to include. What instrument am I using when speaking? For everyone. The vocal tracks. My personal take is that we should include vocal tracks in the latent space in the AI of today, so we can leverage this prior information that we know, that we have, to improve the way that we can clone voice, or whatever we want to do with voice. I'm gonna explain to you what we are doing. It's not an RT, it's not just cloning voice. It is related to detecting in an early stage the Parkinson's disease. What we do is that we try to have a lot of information of Parkinsonian speech, but that's not very common because we need to have patients and we need to ask them to come to the hospital and things like that. My research, what I'm doing, is that I am trying to use a mathematical model of the vocal tract, that is, a model that exposes the position of the tongue, the position of the vocal tract, or the glottis, the fundamental frequency of my voice, to being able to determine how was someone's vocal tract configuration positioned when he or she said something. I know that was really difficult, but I'm gonna repeat it, and I'm gonna show you a demo, so it's gonna be more clear. When we think about the physical model of the vocal tract, the mathematical model, I'm thinking about this. I mean, don't laugh because it can be a little bit stupid, but this is math in reality. This is just a graphical user interface, but there is math behind. This is the position of the tongue, or a cavity. We can feel constrictions, the nasal cavity, the lips. Then we can So, I know in my field, this is just off topic, but in my field, you can do a lot of good things for the, a lot of nice things for the good, and a lot of stupid things to just have fun. But in this case, what we would like to do is that this ping trombone, this is the name of this model, this ping trombone mimics the configuration of someone else, human. And that's something that's not research. And that's something that we can get more or less with more or less precision. So for example, I'm gonna show you me cloning my voice with ping trombone. This is me.
Me llamo Mateo.
And this is the ping trombone saying exactly the same.
Me llamo Mateo.
So it's not cloning my voice because it's a different voice. It's just cloning the positions of my articulators. That means that I don't need to have any cumbersome system like magnetic resonance while I'm talking, or patches placed somewhere here. No, I just need to copy it with this kind of models. And now I can use it to have a lot of new data. For example, a lot of new data of Parkinsonian speech, to help the people, to help the doctors, medical doctors, to understand if someone is in an early stage of Parkinson's. I've known Frank Sinatra.
My funny Valentine.
More or less. But we have the articulators of Frank Sinatra. You can see them live. It's a bit weird. Here when we use it in the graphical user interface, sometimes it's very fast, sometimes it's very slow. I think it's because of my computer being yeah, it's very slow. And but yeah, that's because my RAM memory is tolerant. A lot of demonstrations at the same time. But yeah, you can see where the research is going, and this is what it will come out. This is what I'm so proud of. And that was everything. So today, what we have learned is that first, audio, sound, is massive, challenging, we are very precise, and only trace of people get into that. Second, related in space, this idea of coding and encoding is one of the main ideas for producing new novel audio. It's not an idea. I haven't gone into the specifics of neural networks or anything like that. I just wanted it to be high level, but this is one of the main most important ideas. Speech, super important. And my personal take, I think that synthesis is the future, and if not, here, I'm happy. Where is my postdoc effect? And now, if you have any question or if you want to get into any detail, please let me know.
Question, comments, thank you, Mateo, for this. Let's take that left. Question, comments?
Entonces, ¿puedo hacer la pregunta?
Sí.
Entonces, yo no tengo nada que ver con la ingeniería, entonces es una pregunta general, pero la cosa cómo funciona de la inteligencia artificial. Tú consigues reproducir una voz o lo que sea, X, o un comportamiento o lo que sea. Sí. Entonces eso es con una fórmula, con algo matemático, ¿no? Una fórmula grande. Entonces luego eso lo aplicas a un trocito de tus cosas. Y luego eso lo pones en abierto, o sea, lo pones en la inteligencia artificial. Te estoy preguntando con mis palabras,
Sí.
como el esquema general de cómo eso luego llega a ser inteligente. No lo sé.
Sí, tu preocupación es quizá que la palabra inteligente, como tal, porque
No,
esto es solo
no,
matemático.
o sea, que no sé nada.
Ah, vale.
Estoy en otra, yo soy behavioral economist.
Vale.
Entonces, ojo, patterns de comportamiento de personas y luego lo quiero aplicar a cosas que estoy intentando entender desde tu lado para luego aplicarlo a la vida. ¿Sabes?
Eso es muy interesante. Eso se podría llegar a aplicar también.
Hombres, estoy ahí.
Claro.
Por eso quiero entender el esquema general, para entenderme yo también cómo puedo trabajar.
Mira, lo primero que necesitamos son muchos datos.
Vale.
Eso entiendo que sí que lo tienes, porque manejamos muchos datos. Estos datos son los que nos permiten modificar los parámetros de ese algoritmo matemático
Vale.
para que repliquen los mismos patrones que siguen los datos.
Cuando dice algoritmo matemático es una fórmula.
Es una red neuronal. Pero una red neuronal en realidad es un algoritmo matemático, vamos a llamarlo algo así como un montón de fórmulas encadenadas, pero que se pueden modificar fácilmente, ya no es algo tan complicado, y que al final tenemos unos resultados que nos parecen un plazo. No vamos a pensar en términos matemáticos, porque en realidad ya casi nadie piensa en esos términos, salvo que estés haciendo una investigación. Claro, necesitamos muchos datos para que podamos modificar estos parámetros, que se hacen con código, para que pueda replicar los comportamientos de estos datos. Ahora, si yo soy capaz de replicar los comportamientos, también puedo generar nuevos datos que a su vez repliquen ciertos patrones. Eso se llama la inteligencia artificial generativa. También puedo tener inteligencia artificial predictiva. Es decir, hay un nuevo dato, nuevo porque lo he conseguido hace 5 minutos, y quiero saber qué tipo de patrón está siguiendo. Pues también lo vamos a utilizar para eso. Entonces, mi consejo, digamos, es si quieres aventurarte en este mundo y si quieres utilizar este tipo de algoritmos, sobre todo, tener muchos datos. Sí.
Y contratar a alguien como tú, porque
Sí, si lo mío falla, pues estaré de todo, claro. Sí,
Es que, si me permite, todo esto va también. Yo me acuerdo cuando se empezó a hablar de lo de las redes neuronales, y ya decía muy supera, o sea, no, sí, supera, lo está superando día a día, no obstante, tengo el disco duro ya, los jóvenes me cojan la batuta, ¿no? Porque es brutal, todo esto cada vez más sale, redes neuronales, o sea, miles de datos encadenados, empezando en neuronas, los contactos, y la transmisión rápida. Sí.
Sí, hay arquitecturas, cada día se dan arquitecturas nuevas, para cosas distintas, que mejoran ligeramente cierto parámetro. Bueno, pues es complicado esta actividad. Estamos...
La neurocomunicación, la arquitectura, no sé, yo soy catedrático de arquitectura computacional. O sea, es que solo la palabra te asusta. Arquitectura computacional. A ver.
Abrimos un poco más técnica, que es, o sea, me sorprende porque nosotros en mi grupo lo que hacemos es también AI for Science, entrenamos modelos con datos muy exactos y conseguimos algo que es 99,9% similar, sí, pero en vez de conseguirlo en 3 días es el media hora. Entonces la aceleración es por 1000 o por 2000 y es brutal. pero ese dato que conseguimos no lo reutilizamos para entrenar nunca porque no es 100%, no viene de unas ecuaciones de cuántica tal, sino es de un modelo que hace eso al 99,9%. Y ese dato me sirve para decir que da 2, pero no para reentrenar algo porque ya en cada iteración voy perdiendo. Entonces me sorprende que de la bot tú puedas utilizarla para generar datos, nuevos datos, reentrenar y que eso siga mejorando.
Sí. Esto ha sido un comentario de revisor 2 de paper, ¿sabes? No, calla.
No, porque no entiendo, o sea, obviamente la bot es otra cosa. Es otra cosa, o sea, porque yo ahora estoy generando muchos millones de datos que no generaba antes muy rápido, pero los tengo delante y no los puedo reutilizar.
Sí, es cierto. Mira, pero ¿has hecho alguna vez técnicas de aumentación de datos?
No.
¿Sabes que, por ejemplo, en imágenes es muy normal, tú tienes una imagen con la que quieres entrenar, pero puedes coger esta imagen y inflar?
Sí.
Puedes coger esta imagen y voltearla, puedes hacerle muchas perrerías. Y esto en realidad, a ver, habría que comprobar si no estamos cayendo en un sesgo inductivo, como el que tú estás diciendo, pero mi hipótesis es que al haber tan pocos datos, creo que alguna mejora sí va a haber. Pues,
Y la segunda era en cuanto a conseguir datos. O sea, ¿cuánto necesitas de una conversación de una persona o de una canción para que entrenando eso suene que digas, este...
sí.
¿Sabes eso que clonan las voces de Biden, Trump, etc? Porque tienen un montón de datos, ¿entiendes?
Mira, te puedo decir, el estándar de la industria, que lo tiene una empresa que se llama Eleven Labs, puedes poner tu voz con ellos, ¿tá? Te piden media hora de trabajo. Varía. Procura no siempre muy nunca. Yo, siguiendo lo que hacían ellos, pues cloné mi voz con mi propio sistema, que funciona peor que el suyo, claro, yo solo lo publico. O sea, y ya ves que tiene artefactos y que se nota que es mi voz, pero no es perfecto. Ahora, si tú tienes miles de horas de grabaciones, ¿sabes? De políticos o que sea,
Sabemos. Es de edad también.
pero es que sí que puedes llegar a clonar la voz. Media hora es la clonación, digamos, canónica, reentrenando todo el sistema y tal. Luego puedes llegar a hacer clonaciones extrayendo ciertos parámetros de la voz y insertándolos directamente en la red neuronal sin reentrenar. Con eso puedes hacerlo con 30 segundos. Lo que pasa es que todavía se nota, pero cada vez estamos más cerca.
Sí.
Y es un problema bruto.
Sí.
Te pueden clonar la voz y luego pueden llamar a mis padres, por cierto, que están aquí viéndome, diciendo que estoy secuestrado, ¿sabes? Y con mi voz diciendo, ay, sí.
Bueno, en primer lugar, muchas gracias por la presentación, fue fantástica. Yo tengo una curiosidad. ¿Crees que con estos sistemas se pueden llegar a escribir de forma automática obras literarias, como el Quijote?
Lo que pueden hacer estas inteligencias artificiales son fast teach, porque no dejan de ser aprendizaje de patrones de otras personas, otras cosas que han escrito. Tiene que haber precedentes humanos. Por lo tanto, lo que sí que puede haber es mezclas que puedan ser, oye, que las podamos disfrutar. Pero de ahí a decir que tenemos una verdadera literatura nueva, como la que hizo Cervantes cuando escribió el Quijote. No. Okay, I'm gonna read it out loud. Hello, thank you, Mateo. My colleagues and I are developing software for medical appendices. How can this speech generation be used to improve current medical devices and generate voice for deaf, or mute people? I really like this question, and this works my heart when I think that I'm working for this kind of situation. I really like it. What I can say is that if you are not able to speak, or if you are not able to hear, these kind of devices are can. Let me think for some seconds. Because I know there are some devices that mimic the configuration of the vocal tract. I've seen them in the media lab. They have them. The device or the algorithm that I was talking about is just a mathematical algorithm. So my opinion is that definitely there needs to be a connection. So if we are able to very precisely and very fast detect the movements of the vocal tract, then we can place these movements into some logical device that in the end might be used to produce speech for someone who has lost the voice or cloning the voice in a very physical way, very precise way. And for deaf people, I'm not sure. I'm not sure how I can help you. Maybe a way to help is that they can have like a loop, like bucle de reporte, a feed-forward loop. No, not a feed-forward. Retroalimentación.
Reinforcement.
No. Feedback loop. So they can learn if they are speaking in a way that it's not something that we can notice they are doing some mistakes, some errors in the vocal tract. Maybe this kind of feedback loop may help with some device, medical device, or with some like I presented. But yeah, not sure. Very interested. Who are you? Ustedes, alguien, Roberto Carlos,
Una pregunta,
sí.
hablabas del vocal tract.
Sí.
Y no entendía muy bien, o sea, a nivel de modelo,
sí.
tiene que ser el autoencoder. Sí. Y entonces el vocal tract está ahí como en el latent space, o sea, está parametrizado. O sea, ¿puedes desarrollar un poco más?
Sí, o sea, en el espacio latente del autoencoder, lo que tenemos es que intentar, de alguna manera, que sea muy explícito que tenemos las características de la voz. Y normalmente se utilizan distintos encoders o distintas redes neuronales para, esta es para la audición, esta es para la prosódica, esta es para el discurso. Ahora, ¿por qué no una adicional que sea para el tracto vocal? Especialmente pensando en que tienes un algoritmo que te permite tener muchos datos de tractos vocales, que es el que presento ahora. Entonces, si yo con bases de datos de cientos de horas de personas hablando, puedo tener cientos de horas de tractos vocales moviéndose, ¿por qué no? Mi pregunta es, ¿esto producirá una síntesis mejor? No he llegado a tanto, porque ya veis que el tracto vocal, yo todavía no estoy contento con él. Sí que dice me llamo Mateo, pero me llamo Mateo. O dice así como, esto todavía no está replicando bien mi tracto vocal. Así que, pues eso.
Fíjese, también los humanos, por evolución, sabemos casi hasta detectar la mentira. Según la, ¿sabes? Y la emoción te está diciendo sí, sí, y tú dices no, ¿sabes? No. Entonces, ese tipo ya debe ser mucho más difícil, ¿no? Esa sensibilidad.
Sí.
O sea, dependerá para qué tipo de discurso
Claro.
puede ser más útil que para otro.
Puede ser. Es cierto. Es verdad que tenemos siempre la componente de la persona y redes neuronales especializadas justo en eso. En ser capaces de que tu discurso no solamente sea un discurso plano, sino que pueda funcionar o pueda, no sé, de una manera chiti algo. Pero claro, todo al final es tracto vocal. Es que podríamos llevarlo incluso más atrás. Todo al final es neurociencia. Pero bueno, yo estoy aquí.
¿Y eso que sonaba como un mantra? ¿O te has puesto que sonaba como un mantra?
¿Qué es algo?
Ahí pusiste, cuando pusiste el tracto vocal, ahí había unos sonidos de
Sí. Bueno, sí. Es el tracto vocal en una posición estática, pero con una excitación local. Entonces está, ¿cómo se llama? Colin,
Are you expanded to non-humans? Like how close are you talking to dolphins, elephants?
good point. You know what? When I was in London, because I started this research in the Queen Mary University of London, some people were very interested in that. I haven't. I'm not sure why they always claim that, yeah, because we would like to have some fantastic animals for films, and we will be able to replicate for sure the Google Dragon. Yeah, oh, nice use case, but well, yeah, not yeah.
Okay, thank you. En los próximos meses, pero como si sigues en estas aventuras de la experiencia del sonido a través de la comunicación, focalizas solo la voz humana. Sí, ella es la ella es